A toddler absorbs spoken language without formal instruction, yet they will likely struggle through the slow, bottlenecked process of grasping basic algebra. The cognitive demands here are completely inverted. Learning to speak requires processing an immeasurable amount of data. A child must instantly map countless phonetic variations to complex motor controls in the lips and tongue. Algebra contains a fraction of that data, but causes massive cognitive load. This presents a strange paradox. We execute cognitively massive, natural tasks flawlessly, but fail at culturally simple ones. Modern instructional design struggles to solve this because it frequently ignores the mechanism at play, the evolutionary origin of the knowledge itself. Evolutionary psychologist David Geary provides a framework that resolves this paradox. He categorizes human knowledge entirely based on our evolutionary history. The first category is biologically primary knowledge. These are survival-based skills developed over countless generations. Skills like recognizing faces, interpreting basic social relations, and acquiring native speech all fall into this group. The second category is biologically secondary knowledge. This encompasses culturally invented skills that emerged far too recently to influence human evolution. Reading, writing, and advanced mathematics belong here. Instructional designs that treat these categories as identical assume that all learning happens through the same neurological process, regardless of whether the knowledge is evolved or culturally invented. Biologically primary knowledge is highly modular. Our ancestors evolved different survival skills during different evolutionary epochs. Because these neural modules operate independently, the cognitive process to recognize a face shares zero architecture with the process to recognize a spoken word. This gives primary knowledge a defining biological trait. It is instinctively learnable, but functionally unteachable. You do not need a lesson plan to teach a child to speak. Mere immersion in a functioning society provides all the environmental data those evolved modules need to activate and store information automatically. Designing curricula to teach primary skills is a waste of resources. Our biological programming already automates their construction without conscious effort. The decentralized primary modules contrast sharply with how we handle biologically secondary knowledge. For culturally invented data, humans rely on a unitary, general information processing engine. Look at this classroom exercise. Written language has existed for only a few thousand years. The timeline is far too short for humans to have evolved a dedicated neurological writing module. Running information through our general processing engine requires immense conscious effort. It triggers high cognitive load because the brain is forcing data through an unspecialized pathway. We lack automatic modules for cultural data. Acquiring secondary knowledge mandates explicit institutional support, massive educational structures built specifically to facilitate that heavy cognitive lifting. Educational trends often prioritize teaching general problem solving or critical thinking. These concepts serve as the ultimate test cases for distinguishing between primary and secondary knowledge in schools. Consider the equations on this chalkboard. If a novice student is asked to solve the equation x plus a equals b for the variable x, they face a domain-specific mathematical environment. Novices default to a means-ends analysis loop, assessing the current state, identifying the goal, and searching for an operator. Here, subtracting the extra variable reduces the difference. Conversely, an expert bypasses the loop, using instantaneous pattern recognition to perform the subtraction immediately. The means-ends problem-solving strategy itself is biologically primary knowledge. Our ancient ancestors utilized it for basic survival tasks like navigation or foraging. Since we use means-ends analysis instinctively, there are no recorded instances of formal instruction improving a student's ability to use it. In randomized trials, teaching these general techniques fails to produce far transfer, the ability to solve problems in new fields. The bottleneck isn't a lack of thinking skills, it's a lack of domain-specific secondary knowledge. This brings us to the core assumption of constructivist, inquiry-based, and discovery learning models. These models assume that withholding explicit guidance forces students to independently construct higher quality knowledge. Mapping this pedagogical assumption to Gary's taxonomy identifies a category error. Discovery learning mimics the unstructured immersion required to activate primary knowledge modules, but a mechanical failure occurs when this exact same model is applied to secondary knowledge targets, like physics or grammar. Withholding explicit information does not foster deeper independent understanding. It simply deprives our general processing engine of the cultural data required to build mental models. Direct instruction acts as a biological workaround for human evolutionary limitations. Highly structured teaching artificially guides data directly into the secondary processing engine. It bypasses the need for students to invent cultural knowledge from scratch. Proponents of discovery learning argue that students need to construct their own meaning. But humans only automatically construct knowledge when that specific knowledge aligns with evolutionary survival. To transmit culturally invented knowledge successfully, instructional designers must abandon biological mimicry. We have to embrace the explicit structural guidance our secondary cognitive engine demands.